Welcome to physics online session. Today's class we will discuss energy stored in a capacitor. So let us consider let us consider a capacitor of capacitance C is charged to a potential V, okay, and Q be the charge on the capacitor. Okay, so I'm taking one capacitor. uh, this is my capacitor. This is a capacitor, right? So here, what is the capacitance of this capacitor? C is the capacitance of this capacitor, and V is the potential of this capacitor, and Q be the charge. One of the in the capacitor, one of the plate is at a positive potential, another will be at negative potential. That is what is the charge on the capacitor? Q be the charge on the capacitor. This is plus Q and this is minus Q. So, and there exists an electric field between the plates represented from negative to positive charge. This is the direction of the electric field between the plates. Okay. Now our aim is to find now our aim is to find the energy stored between the plates of a capacitor between the plates of capacitor. Okay, so here between the plates of capacitor. Now initially there is no initially these two plates of a capacitor are uncharged. Okay, there is no charge on the capacitor. So I'm gradually adding charges on the capacitor by connecting it to battery. For example, if you connect it to battery, so what happens, this is a positive terminal, negative terminal, so positive charge will appear here and negative charge will appear here. Okay, I'm taking one intermediate state and the process of charging, where the capacitor plates have charges q dash plus q dash on one plate and minus q dash on another plate. Okay, right, this is a positive charge and it is a negatively charged plate. Okay, now this is an intermediate, this is a final state. Okay, this is intermediate state. I'm taking intermediate state where the charges on the plates are plus q dash and minus q dash. Okay, now uh, let us transfer, in this situation let us transfer a positive charge from negative plate dq dash. Let us transfer some amount of positive charge from minus q dash to plus q dash, so that when positive charge is removed, so we'll get negative charge will appear on the uh, what equal amount of negative charge will be there on the negative plate. Okay, uh, let plus dq be dq dash be the amount of amount of uh, charge transferred from one plate to another. Okay, at potential v dash. No, already it is at a potential v dash. So in this situation we are transferring some amount of charge from one plate to another plate. So we have to do work against this field. Therefore, work done will be, so work done, okay, dw dq, sorry, work done dw, small work done, I am transferring a small amount of charge, the work done is also said to be small, so dw is equals to uh, v dash into dq dash. Okay, so by the definition of electrical potential, we have v equals to w by q, and uh, and w work done can be presented as product of charge and potential difference. So from that equation I wrote dw equals v dash into dq dash. Okay, so where v dash is equals to q dash by c, since c equals to q by v or c equals to q dash by v dash, so we can write this expression as v dash is equals to q dash by c. Okay, now substitute the value of v dash here, dw is equals to v dash nothing but q dash by c into dq dash. Okay, why? Because v dash is a variable one, so q dash also variable, but we are integrating with respect to dq dash, so I'm writing the expression in terms of q. Okay, c is constant, c is a, for a given capacitor, c is constant, capacitance of the capacitor is constant. Okay, so here, therefore the total work done, therefore total work done in transferring q charge, from one plate to another can be obtained by integrating the above equation. W is equals to integral dw, so we are transferring initially zero charge and we are placing q amount of charge, so we have to integrate between the limits 0 and q dash by c into dq. So that implies w is equals to, c is constant, integration of q dash is square by 2, and the limits are 0 and q, that is equals to q square by 2c. Okay, this work done, whatever the work done by us will be stored in the form of potential energy. Therefore this work done this work done will be stored this work done will be stored in the form of potential energy. Therefore potential energy represented by u, therefore potential energy u is equals to q square by 2c. Okay, the other forms of potential, u are your q is equals to cv, that implies u is equals to c square v square by 2c is equals to half cv square. Okay, so it can also be written in terms of we have cv and cv, qc, and in terms of vq also we can write it as vq. I want to replace here see here qv form, I want to write it in qv form, half cv equals to q by v into v square, v got cancelled, so therefore equals to half qv. So these are the potential energy expressions, q square by 2v, half cv square, and qv, these are the expressions of potential energy. Okay, this will be stored in the form, this is nothing but the energy stored in the uh, uh, between the plates of a capacitor. Now I'll write an expression for energy density. Energy density is nothing but the energy per unit volume. This is the energy per unit volume. Okay, energy density is equals to energy per unit volume. Energy density represented by u, small u equals to energy by volume. Okay, So for a, I want to write this expression for parallel plate capacitor. So for parallel plate capacitor, parallel plate capacitor, okay. So here C is equals capacitance is equals to epsilon naught A by D, and charge on the capacitor is equals to sigma into A, or sigma charge density is equals charge per unit area. So I want to use this relation q square by 2 relation, okay. From that we'll get the capacitance as no, the energy as U is equals to q square by 2c, q square by 2c, q nothing but sigma square A square by 2c, 2 into epsilon naught A by D, okay. So therefore we'll get U as, for this is for I am taking a particular place for parallel plate capacitor. I want to find out the energy between the plates of a parallel plate capacitor. Therefore U is equals to sigma square by 2 epsilon naught A into D. A got cancelled, okay. Therefore energy, so area into distance will gives us the volume. Therefore U is equals to U nothing but sigma square by 2 epsilon naught into AD by, so this is AD, okay. Therefore volume is equals to A into D, that is why these two will cancel. Therefore the energy density can be represented as the energy density U is equals to sigma square by 2 epsilon naught, okay. So and the next topic is, and next and last topic from this chapter is Van de Graaff generator. Next topic, Van de Graaff generator. Actually it is the scientist name, okay, name of this scientist. So who generated this, who developed this generator. So what is a Van de Graaff generator? What is the function of this generator? It is a machine, it is a machine to develop high high voltages, very high voltages, high voltages in the order of, in the order of 10 power of 6 volts, 10 power of 6 volts, okay, million volts, in the order of few million volts, okay. And these voltages are used in some nuclear reaction experiments to accelerate particle like electrons and protons, okay. That is a function of this Van de Graaff generator. Now we'll discuss what is the principle behind the Van de Graaff generator and its working, principle and working we'll discuss in this topic. We'll discuss first I told what is the function of this Van de Graaff generator. Now we'll discuss what is the principle, how it works, how Van de Graaff generator works to develop high voltages. Okay. How the principle, what is the principle behind the Van de Graaff generator and how it works, how it develop very high voltage, we'll discuss here. And this is a principle. Now we'll discuss a principle. Let us consider let us consider a large sphere. Let us consider a large large sphere of radius capital R, large sphere of radius capital R, radius capital R, okay. Now let us and Q be the charge on the capacitor. Q be the charge on the capacitor. Okay, no, this is a large sphere. I have taken a large sphere, so large conducting sphere. This is a conducting sphere. So this is a conductor, this is a conducting sphere of thickness, this is the thickness of this conductor, and I place positive charge on this conductor. So we know that whatever the charge given to the conductor resides only on the outer surface of the conductor, because if the charge try to go into the surface, there will be a repulsive force. So it try to minimize the repulsive force. That is why they will stay on the surface of the outer surface of the conductor only. Okay, that is the reason why the charge resides only on the outer surface, to minimize the force of repulsion. Okay, now mm, what is the uh, what is electric sorry what is electric potential? Electric potential on and inside the sphere. Okay, so electric field on the surface, and we are writing electric potential, not a field. Therefore electric potential on the surface and electric potential inside the surface is always constant. Electric, we have discussed in the electrostatics of conductors that the electric potential throughout the volume of the conductor is constant, whether you if you take a point on the surface or inside the surface, inside the shell, inside the conductor, whether you take the surface of the conductor or inside the conductor, the electrical potential is constant. And what is the electrical potential on the surface of the conductor? It is of a sphere of radius r, 1 by 4 pi epsilon naught q by r, where r is the radius of the conducting sphere. Already we have discussed this expression. Okay, right. Now this is electrical potential due to this large sphere. Okay, now somehow what I'm doing here next, now somehow I introduced a large sphere, no, a small sphere. This is a sorry I'll remove some disturbances there. Okay, right. Now somehow I introduce a small sphere. This is a small sphere of radius smaller. So small sphere of radius smaller into the larger sphere, and I have placed at the center. Let small q be the charge on the small sphere. Okay, now what is electrical potential due to? Now I want to find, this is electrical potential due to uh, capital Q. Okay, now what is the electric potential due to small q? Okay, electrical potential due to small q. Okay, so now electrical potential due to small q equals to v equals to 1 by 4 pi epsilon naught 1 by 4 pi epsilon naught q by uh, capital R. This is electrical potential due to a small speed small charge at a point on the surface of a big sphere. Okay, now I am calculating the electrical potential due to small sphere, but at what distance at any point on the surface. So that will gives us q by r, 1 by 4 pi epsilon naught q by r. So it is at or on the surface on on the sphere of radius r, on the sphere of radius on the sphere of radius capital R. Now we'll find electrical potential due to uh, electrical potential due to same sphere on the surface of a small sphere q by capital R. So on the mm, now this is the electrical potential on the sphere the sphere of radius, small r. Okay, now I'll find now electric potential at r, okay, which is on the surface of a bigger sphere due to due to small q, due to small q and capital Q, due to both the charges. Okay, that is V of r. I am calculating the electrical potential on the surface of the bigger charge due to both the charges. So what is electrical potential due to small charge? 1 by 4 pi epsilon naught due to small charge is at the distance on the surface of radius r is q by r plus 1 by 4 pi epsilon naught uh, capital Q by R. Okay, let it be equation number 1. This is electrical potential due to plus Q, and this is electrical potential due to small q at a distance R, which is on the surface of the big sphere. Okay, so both are calculated at the same distance. Okay, next now electric potential at small r, electrical potential at small r due to small q and capital Q is given by V of small r is equals to 1 by 4 pi epsilon naught 1 by 4 pi epsilon naught q by due to small q at a distance r is q by small r plus 1 by 4 pi epsilon naught capital Q. Electrical potential due to capital Q is constant everywhere, so it remains same. Okay, so therefore now I want to find out what is the potential difference between a smaller and bigger sphere. Okay, this is now I want to find, I calculated electrical potential at r and electrical potential at small r. No, I want to find out the potential difference between the smaller and bigger spheres. Okay, therefore the electrical potential difference difference between two spheres is given by so v of r minus v of capital R is equals to, what is the difference here? So I'll write the next step, better to write next step on the next page, is given by, okay, I'll write here v of small r minus v of capital R. V of small r is equals to 1 by 4 pi epsilon naught okay, is common from all the terms. So from second equation, v of small r equals to q by r plus q by capital R, okay, minus 1 by 4 pi epsilon naught into what is v of capital R? V of capital R is this one. So 1 by 4 pi epsilon naught q by capital R plus q by capital R. In both the cases we have q by capital R plus capital Q by capital R. Okay, here q by capital R got cancelled. So what do you get here? Potential difference between the two spheres is given by of r, v of small r minus v of capital R is equals to 1 by 4 pi epsilon naught q by 4 pi epsilon. Q is also common, we have these two terms. Okay, so and 1 by r minus 1 by capital R. Here q is positive. Okay, so and r is less than capital R, therefore 1 by r minus 1 by r is equals to positive. Okay, so this gives us that, so the vr minus v of small r minus v of capital R is equals to positive. So from this expression we can say that v of r definitely will be at higher potential, therefore small sphere is said to be at a higher potential. Small sphere is said to be at higher potential. Okay, now look at this. Now try to understand how many charges, 1 2 3 4 5 6 7 8 9. 9 charges are there, 9 charges here. Number of, for example, 90 charges are there. Let say 90 charges are there. Say 9 charges, 90 charges. So now what I did here, so I connected these two spheres with a somehow I connected these two spheres. When you connect these two spheres with a metal rod, okay, when you introduce into the sphere, I'm using an insulating stand, but when you I want to no, see here, already represented in the figures, no, these two are connected. Okay, so this small q and a small sphere and big spheres are connected with the help of a conducting wire. This is a conducting wire. When they are connected with the conducting wire, what happens here? Flow of charge takes place. So what do you think here? I told that here there are large number of charges, here less number of charges. What do you think when you connect the two spheres? You may think that you might think that the charge flows from uh, a big sphere to large sphere to small sphere. Why? Because large sphere has more charges and small sphere has less charges. Okay, but it is not true. So we know that the charge always flows from high potential low potential. Okay, even though the large sphere has large amount of charge, but it is at lower potential. Already we have derived here. So here what we got? V of r. V of r is the potential at a small sphere. So and V of capital R is at the potential at a capital capital Q R, potential at a large sphere. So we can say that from this expression, the smaller sphere is at higher potential, larger sphere is at a lower potential. So a charge always flows from small sphere to big sphere. Whatever the amount of charge may present on the big sphere or large sphere, charge always flows from small to big sphere. So example, best example, there is a water in the dam and there is a water in the river. So even though the river contain large amount of water, the water cannot go from river to dam. Why? Because if the dam has a less amount of water and uh, river has large amount of water always flows from high potential region to low potential region, dam to river only. So even though the water in the river is large, so it cannot huge, it cannot flow from river to dam. Okay, why? Because in the same case here also the charge flows from high potential to low potential only, and this is the principle behind the working of a vande graff generator. Okay, so here we add charges, somehow we add charges to small sphere, and if you connect it to a big sphere, so automatically flows out, it stay on the outer surface of the sphere. So till uh, how long you supply these charges, till it applying breakdown limit. Okay, so surrounding, if the surrounding air is air, so you can apply only 3 into 10 power of 6 uh, if the electric field reaches 3 into 10 power of 6 volt per meter, then so whatever the extra charge given to the sphere will be leaked out. Okay, so beyond this limit we cannot charge it, we cannot increase the electric field. Okay, yeah. So and this is the schematic diagram. How this is the schematic diagram, this is a working how the charges are uh, placed on the outer sphere with the help of a small sphere. Okay, this is a schematic diagram. Here there is a metallic brush. Okay, so delivering charge from the source, there is a source of charge not represented here, so that is supplying positive charges with the help of a metallic brush. There is a metallic brush which supply to the belt. Here this is a metal belt is there. Okay, so here insulating belt which can carry charge, but will not be stored on it. So here it is a insulating belt, so which carries, so and this belt is moving through the uh, uh, pulley, and when it is rotating, it reaches the other, and it reaches the center of the small sphere. So and there is a connection between the small sphere and large sphere. So due to this, charge flows from smaller sphere to bigger spheres gradually, charges accumulate on the larger sphere until the breakdown limit reaches. So this is the working of a van de Graaff generator. Thank you.